All right, so first section we're going to look at is section 1.1. We pretty much go in order. So of the sections, we don't really skip around too much. Might be a couple sections here and there we skip, but we'll pretty much just go right in order in the book. So the first section talks, the first thing they talk about is just the kinds of numbers that we work with. So I just want to make sure that if I say to you, I'm looking for an integer answer, or I'm looking for a real number answer, you have an idea what I'm talking about. So I'm not going to write down the definitions of every single one of these, but I'll tell you what it is. If you want to make a note, you can, but that's up to you. So we start with the innermost box. Okay, those are the simplest numbers, working our way out to more complex numbers, more theoretical numbers. So counting numbers are the simplest numbers you can have. Okay, they start at 1, and they don't include fractions, decimals, negatives, or 0. So just think of how you would count. 1, 2, 3, 4. And they go up by ones. Okay, so those are the counting numbers. Now, with each new set, whole numbers, integers, rationals, usually the reason why we have these other sets of numbers is because if we only had counting numbers, there are certain things we couldn't do. For example, 3 minus 3. Well, counting numbers start at 1 and they go up. So, Shai, if I did 3 minus 3, what do I get?
0.
0. Well, with counting numbers, there's no such thing as 0. So, if in your brain all you understand is counting numbers, you'd have to say 3 minus 3 is undefined. You can't do it unless you invent a new number. We call it 0, and that gives us whole numbers. So whole numbers are exactly the same as counting numbers, except now you have 0, and now you're allowed to do a problem like that. So with each number set we invent, we can do more kinds of problems. So whole numbers, no fractions, no decimals, no negatives, just 0 and up. All right, so we could still run into a problem. If I had a whole number like 5 minus 8. Okay, if I do 5 minus 8, Isabel, what would I get when I do that?
-3.
Yeah, I get -3. So if all you understand is whole numbers, what she just said makes no sense, right? Whole numbers, there's no such thing as negatives. Negatives don't exist. So maybe someone in first grade would write a question mark, or they'd put, I don't know, because you can't take away more than you have. Like if you think about it practically, if I have $5 and you say, oh, can I borrow 8? I don't have 8 to give you, I have 5. So that's where we invent negative numbers. Okay, so that's what integers are. So now with negative numbers, we can solve that kind of problem. Before negative numbers, you can't. But even with negative numbers, we can still run into a problem with division. If I took something like 3 divided by 2, well, that's like saying if I'm holding 3 things and I want to distribute them equally to 2 people, I can't do that. I have 3 things. Like, how do I distribute them to 2 people? I can't because it's a fraction, okay, or a decimal. And that's where rational numbers come in. So now rational numbers include positives, negatives, fractions, decimals. And for most everyday purposes, rational numbers are about as complicated as the average person, I'm not talking an engineer, like an average person would use. And now with rational numbers, we don't have to write question mark. We have a thing called a decimal, and we could answer what is 3 divided by 2. Okay. So I have rational numbers written out a little more formally. I thought I did. No, it's fine. Okay, so rational numbers are basically fractions. Okay. So that's a rational number. Okay, that's a rational number. Okay, that's improper, but it's fine. It's still a rational number. So if rational numbers are what you can write as fractions, then irrational numbers are, how do you think we would define those?
Not be written as fractions.
Yeah, irrational numbers are numbers you can't write as fractions. Okay? They're decimals that go on forever, but they don't repeat, and there's no pattern. So if you said, well, what about 0.3333333? No, that's rational because it's 1/3. That repeats. Can anybody think of a number that's a decimal that doesn't repeat? There's no pattern to it. Can't write it as a fraction. Yeah, Jake, see you pointing?
Pi.
Yeah, pi. So pi is an irrational number. Also, numbers like square root of 2. There's no repeating pattern over and over. In fact, the square root of any number, that's not a perfect square. So if you did like square root of 9, no, that's not irrational. Square root of 16, no. But any number that's not a perfect square. So there's one example. And if you're wondering, well, maybe someday could we figure out a fraction? Like somehow, maybe with better computers and stuff, could we ever get a fraction for that number you're seeing on the screen? The answer is no. I could prove to you it's impossible to ever write the square root of 2 as a fraction. Can never be done, ever. Okay. All right, so now you take all the numbers you can write as fractions and the ones you can't, and together we call those the real numbers. And that's what you study in Algebra 1. Okay? And that's most of what we're going to look at throughout the year. There are numbers that are not real. Does anybody know what those are called? Yep, Nathaniel.
Imaginary numbers.
Yep, those are your imaginaries. And if you're like, well, why do we have them? Same reason we have whole numbers. So we can do something like that. Okay? Same reason we have integers. So we can do something like that. Well, this problem with the question mark is just like all the other ones. Unless you're going to invent something to give you the answer, you just have to leave it as question mark, because there's nothing you can answer this question with what I have on the board right now. We have to get into imaginary and complex numbers. Okay, so that's a separate diagram. I'm not going to put that up, but I just want to let you know there's more than just real numbers. Now, if you think of these numbers as places, starting like really specific and then getting more general, think of counting numbers as Boston, like whole numbers Massachusetts, integers the Northeast, and then rational numbers the US. If you're in Boston, are you automatically in Massachusetts? Yeah. How about the other way around? If you're in Massachusetts, are you automatically in Boston? No. That's how this diagram works. Okay? If you're a counting number, you're automatically everything else. Okay? If you're a counting number, you're automatically a whole number. You're also automatically an integer. If you're in Massachusetts, you're automatically in the Northeast. If you're in Massachusetts, you're automatically in the US. Assuming there isn't like another Massachusetts in another country somewhere else. Okay, but things like that. Or another Boston somewhere else. Right? But that's how the diagram works. Yep.
Is irrational Puerto Rico?
So irrational, sure, it could be another, well, let's just say if I said rational numbers were the US, maybe irrational numbers are Canada, and then real numbers would be like North America. Although I forgot Mexico now, but I'm doing the best I can. All right, so that's the idea with real numbers. So we have some symbols to represent a few of these sets, 3 that I checked off, and those are the symbols that we use. I think the R for real, that kind of makes sense. The Q for rational, if you think of when you divide a fraction, the answer is a quotient. Kind of makes sense, so Q for rational numbers. Although it's a Q with kind of this extra line in it, it's just how they draw it. And then Z for integers. And the Z, I have no idea. So it's the symbol they use for integers. And now you can modify these slightly. So if I did something like, say I did something like this. Put a little plus sign. What kind of number do you think I'm talking about if I had a Q with a little plus sign next to it? Yeah.
Rational positive number?
Yeah, a positive rational number. Okay? Or if I wanted to talk about negative rational numbers, I could do something like that. Okay. Questions on those symbols? All right. All right, so kind of an obvious fact here, but in math, there's 4. Binary means 2, right? Or bi means 2, and nary number. So there's 4 operations, basic ones in math, that require 2 numbers to make it work. And that's add, subtract, multiply, and divide. You can't do addition, subtraction, multiplication, and division with a single number. You can't write down 3 plus and say, what's the answer? You've got to have another number there to make it work. That's a little different than something like a square root. Square root, I don't need another number. Okay, square root, just give me a single number, that's all I need. But add, subtract, multiply, and divide, you need 2. So we'll look at some basic properties, like the commutative, associative, distributive. So we're just going to look at some of those properties. I think most of them you'll be familiar with, but there might be one that's a little new. Now, to describe these properties, I'm going to use variables, a, b, and c. And when I use an a, a b, or a c, it can represent any real number. So positive, negative, fraction, decimal, 0, anything like that. And the first property we're going to start with is closure. I think commutative, associative, distributive, people have heard those terms even if you're not 100% familiar with what it is. But closure is one we don't hear about as much. Does anyone know what closure means? Yeah?
Close something out.
All right, so like if you like block something out or like close the door, it blocks out what's in the hallway. Trying to think how to relate that to the math definition. It's a little tough. Anyone have any other ideas about closure in math? Kind of has to do with that number diagram I had before. Okay.
Security, like a guarantee that something is or isn't something?
Yeah, it does have to do with a guarantee that something happens or doesn't happen. So the idea with closure, let's take counting numbers. Okay, so pretend other numbers don't exist. We're looking at numbers 1 and up, no fractions or decimals. If I take a counting number, how about Isaac? Can you give me a counting number? 7. Okay, and I'm going to do this with addition. Okay, so I'm going to do 7 plus, and Nick, can you give me another counting number? 8. And if I add those together, Nick, what do I get? I get 15. Is 15 a counting number?
Yes.
Yeah. So closure basically means that if you have an operation, in this case addition, if you take a counting number plus a counting number, the answer has to be a counting number in order for closure to be true. So that always works. You could give me any counting number plus any other counting number, and the answer is always a counting number. Now, let's change it to subtraction. I have a counting number minus a counting number. If you want to know if subtraction, if the property of closure works for subtraction, ask yourself, is that counting number minus that counting number, does that give me a counting number? What do you think here? Yeah. No. So for counting numbers, the property of closure doesn't work with subtraction because you can subtract 2 counting numbers and get something that's not a counting number. The property of closure would not work for division. You can take a counting number, divided by a counting number, and get an answer that's not a counting number. So the idea is you have to take 2 numbers in the same set, and the answer that you get is also in that set in order for closure to work. Okay. Questions on that idea? All right. So kind of just writing out what I just said. Closure, this is for addition, always works for real numbers. Always. If you take a real number plus another real number, I guarantee you always get a real number. Okay? So the answer that you get is in the same set as the two things you started with. Okay, that's probably the most confusing property to try to explain. All right, so commutative. If you look, just pronounce the beginning of that word, commute. Like if you commute, that means you go from one place to another, commute to work, commute to school. Commute has to do with moving things around. So again, all of these properties are for addition. If you're thinking, well, doesn't that work with multiplication too? Like 2 times 3 is the same as 3 times 2? Yep, but we're not looking at multiplication, just addition. So A plus B equals B plus A. Associative. Well, again, think of it like the word associate. If you have a bunch of people that you associate with, you might call that your, what would you call all those people you associate with? If you want to describe all those people, that's your group, right? Your group of friends or your group of people you talk to. So associative has to do with how you group things. And in math, what symbol do we use to group things?
Parentheses.
Parentheses, yep. So notice the order is the same. ABC, ABC. But on the left, I've grouped B and C, and on the right, A and B. So you could try that with actual numbers, and it works. Let A be 1, let B equal 2, and C equal 3. Right, so you can change the order, or the grouping, not the order, sorry, the grouping you do things in. Okay, with addition. Identity. So the identity is something you can do to a number and get the same number back. So for addition, what would that be? What can you do to a number and get the same number back? It won't change it. Yep, Michael?
Add 0.
You can add 0. Now there's also an identity property for multiplication, but it's not multiplied by 0. Okay? It's multiplied by 1. So the identity property for multiplication is a little different than addition. But it's the same idea. What can you do and get the same thing back? Inverse. So inverse is what you can add to something to get 0. So basically we would just say you can always add the opposite. Take a number and add its opposite, you get 0. It's called the inverse property. And distributive. Well, distributive is basically when you have parentheses, you could have addition, or it also does work with subtraction. And you take what's on the outside and distribute to what's on the inside. So, A times B, copy the plus sign down, A times C. Okay, so any questions on any of those properties? Okay, so I'm not going to go through and write them all again, but on page 2 in your book, there's all the same properties for multiplication. So it would say something like A times B equals B times A. 2 times 5 equals 5 times 2. And they go through all the properties. All right, so an equation. In order to have an equation, what symbol do you have to have? Like if I have this, that's an expression because it's missing the symbol that I'm thinking of. Maddie?
Equal sign?
You got to put an equal sign and put something on the other side. So an equation is basically an equal sign between two expressions. And what I have on the board there are 3 types of equations. These are all equations. We'll talk about what each one is called. Let's start with 5 equals 2. So how could something like that happen? Let me just make a small change to this. In Algebra 1, if I gave that as a problem and asked someone to solve it, they might say, oh, subtract 3x from each side, and then that cancels, and you get 2 equals 5. That's how something like this could happen. So 5 equals 2. Any thoughts about that?
That is not complete.
It's not what?
Complete.
What do you mean by not complete?
You have to add something to either the 5 or the 2 to complete it, to make it make sense.
Well, let's say that it was this equation right here, and you did everything you could. You subtracted 3x from both sides, so mathematically that's all you can do. There's no other arithmetic here. We just kind of have to look at that and now basically say something about it. Yeah?
It's improper.
Okay.
5 can't equal 2.
5 can't equal 2. That's a contradiction. So that comes from an equation that can't be solved. 3x plus 2 equals 3x plus 5. You'll never be able to solve that. It's impossible. So that's an equation that's a contradiction. Now, this one, 3 plus 4 equals 2 plus 5. What's going on there? Yeah?
Well, the statement would be true because both sides add up to 7.
Yeah, so that'd be kind of like if you had a problem like that. 3x plus 2 equals 3x plus 2. If you move all the variables to one side, they cancel. And you get 2 equals 2, or 7 equals 7. Well, that's an identity. So an identity is an equation that is always true. So you could pick any number you want for x in this equation in the box, and it would always work. 2x equals 12. Is that always true or always false? Or is there a third option? What do you think? Yeah?
It depends on what x equals.
Right, there's a condition. X could be true if you pick the right number for x. So that's a conditional equation. So it's an equation that could be true if you pick the right number for x. An equation that's never true, contradiction, and then an equation that's always true no matter what you pick for x, an identity. Any question on those 3 types of equations? All right, so now let's go through some steps, and you know what? Let's do it this way. I have an equation on the board: 2 and then in parentheses x plus 3 equals 6 plus 2x. So what I'm going to do is I'm going to show you the first step, and then I want you to tell me the reason I can do that. Okay, it's going to be one of the properties that we've talked about: commutative or distributive, things like that. So I'm going to start by doing this. Okay, so what property allows me to do what I just did right there? Yeah, Jake?
Distributive.
That's distributive. All right, so that would be like a blank on a test, and you'd have to fill in distributive property. All right, the next thing, let me write down this part. It's not really a super fancy term for what I just did, but what did I do to get from the step above to the one below? Yeah?
Multiply?
Yeah, I just simplified it. Okay, bless you. I just multiplied 2 times x and got 2x, and 2 times 3 and got 6. So there's really no fancy name. You just simplified. You did out the arithmetic. All right. And now I'm going to do this. What would allow me to go from step 2 to step 3? Yeah.
Would it be commutative?
That's commutative. Okay? The right-hand side is not changing the whole time, so you don't even need to look at that. It's just the left. I went from 2x plus 6 to 6 plus 2x. I changed the order. So that's commutative. Okay. Any questions on example 1? And that's it for that. All right, so now we'll really quickly go over coordinates. We'll start with like a one-dimensional number line, and then we'll get into two-dimensional with x and y axis, and name, which directions are positive and negative, but we'll go through it real quick. So, single-dimensional coordinate system, just a number line. It's a single axis. Positive numbers right, negative numbers left. 0, right at the origin. And with the idea of a number line, now we can start to compare numbers to each other. Okay? Like if a number is bigger or smaller. All right? So anytime a number is to the right of another number, it's always bigger. Okay? If a number is to the left of another number, smaller. Can anybody think of the names as 4 symbols we use to compare numbers? Yeah.
Greater than, less than.
Yeah, so we have the greater than, the less than, and the other two. Yep.
Greater than or equal to and less than or equal to.
Greater than or equal to, less than or equal to. And those 4 symbols, those are your inequality symbols. Okay. So this is what I just said. Using a number line, you can start to order and compare numbers and say like 3 is bigger than 2. And if you think about it, like numbers themselves are kind of weird. If I said to you, show me 3. Show me 3. Well, that's 3 fingers, but that's not 3, okay? This is how we write the number 3, but what does that really represent? It represents 3, which is just kind of a abstract idea, 3. I mean, there's no reason why you couldn't use that symbol to mean 3. I don't know. It's whoever, well, that gets into the development of language, but with whoever made that symbol, we said, all right, we're going to call this a 3, and it's going to represent the idea of 3. So 3 or 2 or any number, numbers are just ideas. You can't really show me 3. You could show me 3 pencils. You could show me 3 fingers. You could show me how the symbol for a 3, but you can't actually show me 3. Okay? So if you think of numbers, it's just kind of like a game everybody plays, and we all use the same rules. That's all numbers are. Okay? We all know that that's a 3, and we just kind of accept it. So it's this is kind of how numbers work. So 4 symbols there, all called inequality symbols. All right. So when we graph numbers on a number line, we usually put a circle. At least this is one way to do it. I'm going to show you another way in a minute. But we put a circle, and your 2 choices are an open circle or a closed or filled in circle. Which one you use depends on the problem. If the problem has a greater than or a less than, use the filled in circle. If the symbol has that little bit of extra under it, the equal to, then you have to do the extra step and shade in the circle. That's how I remember it. Extra symbol on the bottom, extra step, shade in the circle. And then what we usually do after that is once you put the circle, you end up drawing an arrow either left or right, or sometimes you have 2 circles and you shade between. It depends on the problem. But you have to do some kind of shading first. All right, so let's start with that. Now, if I was asked to graph something like that, I don't really like it written this way. Does anybody know what I don't like about writing it that way? 2 is less than or equal to x. Or anyone have a thought about what I would rather see? That's the same, it's equivalent, but it's written a little different. Yeah, Connor?
Would it be x is greater than or equal to 2?
Yeah, I'd rather see it written like that. X is greater than or equal to 2. They're the same thing, but I would prefer it that way. Does anybody know why I prefer the way on the left rather than the way on the right? Jake? Because of what?
We're looking for it.
Okay, so we're looking for x, and like when you solve an equation, you usually write x equals 2. I mean, you can write 2 equals x, but we normally don't. The other thing is, if you put the variable on the left, this symbol tells you which way to shade. If you put the letter on the right, the symbol doesn't. It tells you the opposite way to shade. All right, so keeping the letter on the left, this will always point in the direction to shade. All right, so let's make a number line. You don't have to number a lot, just enough so I can see 2. And Kylie, what kind of circle would I use in this one? Open or closed? Closed. And what number would we put it on?
2.
2. So, closed circle on 2, and we're shading all numbers that are greater than 2, so we're shading to the right. Some people like to do the arrow above the number line. I don't care if you do it on it or above it. That's fine. Okay, questions on that? Let's look at this one. This is just another example of showing you 2 things that are the same. Given the choice, which one do you think I prefer? The one on the left or the one on the right? The right, yeah. I like that one better. All right, so let's set up our number line. This time, I'm just going to go by 3s. And Emily, what kind of circle do I need this time? Open or closed? Oh, sorry, open. Yeah, I'll make sure I make eye contact with the correct Emily. So open circle, and then on 3, and then Emily, which way am I going to shade? We're going to shade to the left. Y is smaller than 3. Numbers smaller, go this way. Okay, any question on shading with an open or closed circle? So one other symbol we're going to see, we'll do the same 2 problems again, but in place of the filled in circle, our book uses a bracket. Still the same idea, just put a bracket instead of a filled in circle. The only trick is that a bracket can face left or right. You have to make the bracket face the way you're going to shade. All right, so if we remember what we just did, how about Megan? What way did we shade when x was greater than or equal to 2?
Towards the right.
Yep, towards the right. So I'm going to use the bracket that faces the right. So just put a bracket and shade to the right. If the directions in a problem don't say which symbol to use, you could use a closed circle. If you see something like this on a test, and I say, what does that mean? I would be looking for you to write this. You just have to know what it means. All right, and this one, y is less than 3. Anyone have a guess what symbol they might use instead of an open circle? Kind of follows along the same lines as what we just did, but it's not a bracket. Jake? They use a parenthesis. Okay, so our book uses a parenthesis for the open circle. So, same idea. Make sure you put the parenthesis facing the way you're going to shade. So we're going to shade to the left. So parenthesis opening left. Any questions on that? Has anybody ever seen the bracket in parentheses before? Yeah. Sometimes they do it on like SATs or MCAS, starting to do that now too, so you don't have to worry about MCAS. Okay, this one's a little different. This time, it's a compound inequality. You've got a variable in the middle, you've got a number on each side. So this inequality is an and. So the way you read it, you read this part first, 2 is less than or equal to x, and x is less than or equal to 9. Okay. Now, what's in the red box, I wrote that part right there. What's in the black box, 2 is less than or equal to x, I wrote it the way we normally prefer. X is greater than or equal to 2. That's what's in the black box. It's the same thing. So if I graph this, what does that mean about my shading? It's going to look a little different. How's the shading going to look this time? Greta? So x is greater than or equal to 2 and less than or equal to 9.
So it'll be like, wouldn't it be like 2 circles?
Yep, we're going to have 2 circles or brackets, parentheses. And where are we going to shade?
In between 2 and 9.
Exactly, in between. All right, so this one we're going to shade in between. So I just went by 2s. And we can choose if we want to use brackets, parentheses, or the circles. But don't mix them. Just pick one and we'll go with that. Let's do the brackets. So bracket on 2, bracket on 9, shade between. Okay, so again, that's a conjunction. And. Okay, any questions on it? Okay, absolute value. Kind of showed part of it already, but what is absolute value? If you want to think of it like, geometry-wise. Yeah, sure.
It's how many spaces it is away from the 0.
Yeah. So it's basically how far a number is from 0. So that means when we take the absolute value of a number, since it's a distance, how about, Carolyn, what kind of number should distance always be? Or could you think of a number that if somebody said to you, oh, the distance from here to here is this, like a number that wouldn't make any sense at all for distance? Not sure? Anyone help her out? Yeah, Kat?
It should be like a counting number. Like, so if it was like -3, like that's what value would be 3.
Okay, I agree. It can't, so if it was -3, it would be 3. Is it always a counting number? Because counting number means you can never have a decimal. Or it means you could also never have 0. Yep.
It needs to be a positive number.
Yeah, it has to be at least 0 or higher. So if we say positive, it means it couldn't be 0. But we'll just say it can't be negative. Okay, so it could be 0, which is not positive or negative. It could be 0 or higher. All right, so we'll just go through that real quick. Harris, the absolute value of 6 would be 6. And how about Morgan? The absolute value of -3? 3. So absolute value, always positive. Okay, I think we're good with that. Okay, where we use absolute value is to find distance between 2 points on a number line. So if I said to you this morning the temperature was 65 and now the temperature is 90, tell me how much the temperature changed. What math operation do you use? Go ahead, Sam?
Subtraction.
Subtraction. Yeah, you subtract. And because you're taking the absolute value, the order doesn't really matter. So like I said, if the temperature was 65 and now it's 90, you could do 90 minus 65 or 65 minus 90. If you're taking the absolute value, they're both going to come out positive anyway. Okay, so on a number line we have -2, -9, find the distance. Right. So Connor, could you tell me just how to set up my expression?
You do the absolute value and then -2 minus -9.
Yep.
And then close absolute value.
And what's going to happen there when I do -2 minus -9? What's going to happen? Yep.
Well, it changes 9 to a positive.
Yep. So it's going to be -2 plus 9. So I get absolute value of 7. And then the absolute value of 7. 7. Okay. Any questions on that? Okay. So that's how you find distance between 2 points. All right. Now we'll move on to 2D. And then I think after this, we're going to do something on the calculator. All right, so there's all the important stuff in 2D. You have an x and a y axis. X is always horizontal, y is vertical. Where the x and the y axis intersect, that's your origin. For the x-axis, positive is right, negative is left. For the y-axis, positive is up, negative is down. Now I've labeled 4 sections on the board with Roman numerals, 1, 2, 3, and 4. Does anyone know what the sections are called when you draw your axes like that? Yeah, Michael?
Quadrants.
Quadrants, yep. So quadrant 1 is in the upper right, 2, 3, and 4 going counterclockwise. And now, if you want to tell me a certain spot on the coordinate plane, what do you use to describe a location on the coordinate plane? What is it called? Yep.
Coordinate?
A coordinate, yep. And specifically, if it's a 2-dimensional coordinate, that's an ordered pair. Coordinates can also be 3-dimensional. That would be called an ordered triple. So coordinate is kind of a vague term. Just means you have a location. Ordered pair is a specific type of coordinate. It's a 2D coordinate. Okay. Any questions on that? And as far as graphing coordinates, I'm going to assume people are good and can do that. Okay. So zooming on a calculator. So one of the trickiest things to figure out is sometimes you draw something, you sketch something, and you don't see anything on the screen. And that can be because it's shifted off the screen somewhere. So you have to find where it is. Okay, and that takes a little practice. So I'm going to show you how you can change the window or the zoom on your calculator. So first thing you want to do is turn it on. Okay. Once it's on, just to kind of set everybody's the same, I just want you to press zoom and then 6. If you're having something draw on the screen, that's because the last person that used it left something in the calculator. If you don't have anything on the screen, that's fine. Don't worry. I just want you to press zoom 6. And if it drew something, great. If it didn't, I don't care. Now, next to zoom is the button window. So if you press window, everybody should look like this. Okay. Zoom 6 makes the screen go from -10 to 10 on the x-axis, and -10 to 10 on the y-axis. Zoom 6 is where I usually start every problem, and then I change it from here. Any questions on that? Yeah?
I came up with an error.
Came up with an error? Let me take a look. So after a while, you'll get a little better at fixing these errors, but for now, I'll just fix it. All right, you're all set now. Anybody else have an error? Okay. Now I want you to press y equals. So y equals is where you type in something you want to graph. Let's type in a parabola. I'm going to do x squared plus 10. So the x button is right where I'm pointing. It's right below mode. So x squared is the fifth button down on the left-hand side. So x squared, and then plus 10. Okay. Any questions on typing that in? Yep.
This one has an error.
This one has an error.
Yeah.
Is this one yours?
Yeah, that one's actually.
Okay. So you are all set. So x squared plus 10, and then hit graph. When you see the little yellow circle next to the battery spinning, that means it's doing something. Mine just stopped, it's all done. You might think, well, we didn't type anything in. We did. It's off the screen. So I'm going to show you how you can get it on the screen. Let's set our window to be bigger. So instead of -10 to 10, I'm going to go -20 to 20. There's 4 numbers that they're giving you. The names of these 4 numbers are the x-min, x-max, in that order, y-min, and y-max. So we're going to change those 4 numbers. And does anybody remember where those 4 numbers were? What button I had to press? Yep.
Window.
Window. So press window, and now type in the 4 numbers. Yeah. Yours says error? All right, let's take a look.
I tried to do that. Do you have to enter something when you try to do it? Like, do you just like keep
No, but I'm not,
Just
the window is
go-
the
Go down.
Just square
Oh,
plus 10.
they're
x squared is 10.
So let's go like this. Let's take x squared. Okay, now we put plus 10. All right. Now I'm going to try -20. Hit enter. 20, or you can hit the down arrow. And -20. And 20. All right. Once you've typed in those 4 values, if you press graph now, you should see a parabola shifted up 10 units. Okay. How many people got that picture? Okay. Anyone that having trouble getting that picture? So the reason we didn't see it before is because what I'm tracing right now is what you were looking at. You were zoomed in too far to see it. Yep.
I have an error.
You got an error?
Yeah.
So let's take a look. So error window range. Okay, without even looking at it, if you have an error window range, I'm gonna let you try to fix it. I'm gonna go to window, and I'm gonna do something, and watch what I'm doing. See what I just did? And I'm gonna hit graph, and something, it's gonna complain to me exactly what yours did. Do you see what I changed? Watch when I hit graph now. It's exactly the error you were getting, right?
Yep.
You see why you were getting it now?
Yeah.
Okay. Were you able to fix it? No. Why did he get an error when he did that?
One of the values is incorrect.
Okay, not just incorrect, specifically, yeah.
Positive, not negative.
Okay. It is positive. So what's the reason it's giving me an error though? Yeah.
The min and the max is.
No, one's 30 and one's 20. So they are different.
The minimum is bigger than the maximum.
The minimum is bigger than the maximum. You can't do that. So if you type it in like that, you're gonna get a problem. Are you all set now, Harris?
Yeah.
Perfect. Okay, there's so many different ways things can go wrong. Some of the other problems people had nothing to do with what they did. It was because of somebody before they used it, so I just helped them fix it. The other error that somebody had was they typed in this. They just had squared plus 10. Okay, they forgot to put x squared. So if you type that in, you're probably going to get a syntax error, which means you typed in the wrong thing. Another time a syntax error comes up is when people do this. 9 minus 5. How come the calculator can't do 9 minus 5? What's wrong? Well, I'm just doing arithmetic, so I don't need a variable here, but what I typed in is not really 9 minus 5. Yeah.
You type 9, -5.
Yeah, I typed 9, -5. That's minus. So syntax error means you typed in the wrong thing, okay? Or you forgot to type something in. Okay, any questions on that? All right. The other thing before we finish up with our last formula, I didn't mention the scale. Okay? All that the scale does is control how often you see a tick mark on the screen. So if I set the scale on the x-axis to 5, I now will see a tick mark every 5 units. Honestly, I never changed the scale. No. There's not really much reason to. But if you wanted to change how often you see tick marks, you can change the scale. That's all that is. All right. So last formula we'll look at, kind of separate from the calculator, is the distance formula. And if we look at that from Algebra 1 and geometry, we should know where this comes from. Where does that, what formula is this really? The distance formula is just another formula from geometry having to do with a triangle. Yeah, it's just the Pythagorean theorem. This is the length of one leg. This is the height of the triangle. So it's like you've got the length of this leg. You've got the height. Well, if you take those two numbers and you square them, add them up and take the square root, that is giving you the hypotenuse, which is exactly what the Pythagorean theorem is. Finding the distance between 2 points. So that's the distance formula. Okay, so let's try finding the distance between these 2 points. 1, 4 and 5, 6. Now, right now, the 1, the 4, the 5, and the 6, they're not labeled. They're not labeled x1, x2, y1, and y2. So let's label them and then go from there. How about, Alex, what could I label the 1 as? Actually, right now, I have 2 choices.
X1
Could be x1 or
X2.
it could be x2. It's got to be an x. We can pick x1 or x2. I'll let you pick. Do you want it to be x1 or x2? X1. Okay. So now that Alex picked that, everything else is pretty much automatic. Haley, what does 4 have to be?
Does it have to be y?
It has to be a y, and it has to be y1.
1.
The 1s have to go together, and the 2s have to go together. Okay, so now we'll fill it in. All right, so Alec, can you tell me what I write down to find the distance using those numbers?
So you would do square root,
Yep.
and then first pair of parentheses, you would do 1 minus 5,
Okay,
square that,
perfect.
plus another set of parentheses with 4 minus 6 parentheses and square.
4 minus 6, and square. Okay, so 1 minus 5 is going to give me -4. And Shai, what's -4 squared?
4. -4 squared is 16.
16. Yep. So 16. And Isabel, 4 minus 6 gives me
2.
-2. And if we square that, Isaac, 4. So I get the square root of 20. But square root of 20 can be simplified. How can we reduce the square root of 20? Yeah, go ahead, Connor.
If you could take a perfect square out of it,
Yeah. And what perfect square goes into 20?
4.
Yep, so you could write it as square root of 4 times the square root of 5. And you picked a perfect square because you can take the square root of it in your head easy. What's the square root of 4? Connor?
2.
2. So 2 square roots of 5. So any answer that comes up anytime during the year in pre-cal with a square root, if you can reduce it, reduce it. Any questions on it? So again, since that's more of algebra 1, maybe 2 stuff, I really don't spend a lot of time on how to do it, but if you have a question, you can always ask. Okay, and the last one, Bob. A little easier than the distance formula because it doesn't involve square root. So distance formula, the answer is a single number. It's answering the question, how long is something? Midpoint formula is answering the question, where is something? Where is the halfway point between two other points? So the formula is x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. So the answer is a coordinate. Now, look at what you're doing right here and here. You're adding up two numbers and then dividing by 2. There's a name for that. What's that called? You add up two numbers and divide them by 2. It's the, yep, Isabel? It's the average. So the midpoint formula is just the average of the x's and the average of the y's. It's nothing fancy. That's all it is. So we'll finish up by finding the midpoint between those 2 points. Yeah, negative 5, 2, and 3, 7. If it comes out to a fraction, we can leave it. If it reduces, we'll reduce it as much as we can. So let's start with the x's. Rebecca, what's negative 5 plus 3?
5 plus 3, negative 2.
Yep. So we get negative 2. We have to divide that by 2. And Kylie, 2 plus 7?
9.
9. And we're going to divide that by 2. Okay. So when I simplify it, that's fine. Or if you wrote 9 halves as a decimal, what's 9 divided by 2?
4.5.
4.5. Okay. Any questions on that? We covered lots of different topics today. Mostly, I think it was all review, I hope, except for maybe the zooming on the graphic calculator. Maybe you've never done that before. All right, so the homework tonight on page 11, it's 5 through 16, 20 to 23, 28, 31, 32, and 44. Okay, don't forget, I will be after school for extra help tomorrow, if anybody needs it. First test is on Friday. And that's it.